Section 4.6, Elastic Potential Energy. In this section, we're going to talk about another type of potential energy, which is elastic potential energy, which is part of the mechanical energy. If you have tried to play in a trampoline, jumping in a trampoline, seen from the physics point of view, the jumping on a trampoline requires a transformation of the energies. Mechanical energies. So transformation between kinetic energy, gravitational potential energy, and elastic potential energy. During the jumping, springs in a trampoline are stretched and then return to a rest position, and then again to compress, and then return to a rest position, and that continues. But now let's start. What is the rest position? When a spring is unstretched and uncompressed, the force exerted on a spring is zero. So that means the spring is at a rest position. Take a look on that diagram. There's a spring on a frictionless horizontal surface. So there's no force of gravity actually involving, because force of gravity is already cancelled by normal force that is exerted by that surface. So sideways, there's no force. So spring force or elastic force is zero. That means that position of that X, of the object on X-axis, is called a rest position. If that block moves on the left or on the right, then there is no longer a rest position. It is either compressed or stretched. But if there's no force acting on it and the surface is frictionless and force of gravity obviously is cancelled by normal force, that is exactly what we call a rest position. If we want to change the position of the box from the rest position to another position, we apply a force. This time we can label that force as a pull force because we are pulling from the rest position. So we are stretching the spring. And you're going to see that spring is fighting back. The spring is reacting back and trying to restore that rest position, that equilibrium. So while the force is pulling the box on the right, the spring is trying to restore, pulling back the box on the left. So since that we know that right, we label it to be positive on the right, that means that spring force or elastic force is negative. But take a look on the displacement. From the rest position to the new position, displacement is toward right, so that means is positive. So they have the opposite direction. Now let's see if we try to compress the spring. Instead of pulling it from rest position, we push that spring. So we are going to feel that reaction. That spring force again trying to restore that rest position, trying to push back the box toward a rest position. So that means the force, spring force this time is on the right, that means it's positive, and displacement from rest position to the new position is toward left, and we say that is negative. Now take a look. When the force was negative, the displacement was positive, and now in the second case, when we are compressing it, the force is positive and displacement is negative. So it is opposite direction. The relationship between a spring elastic force and its displacement is expressed by Hooke's law. Hooke's law says that the amount of force exerted by a spring is directly proportional to displacement of the spring. So the formula is elastic force is equal minus K delta X, when Fe is elastic force, K is a coefficient of proportionality or spring constant, and delta X is displacement. So why is it negative? We know that when a spring was a positive, direction of the spring force was positive, displacement was negative, and when the spring force was negative, displacement was positive. To make it equal in direction and in magnitude, we use that negative sign. As we learn, a spring exerts a restoring force that is proportional to a displacement from equilibrium or from that rest position. So elastic force is equal minus K times delta X. However, what about speed of a moving object? For this, we do that experiment the same. We stretch the spring with a box attached on it, and after reaching a certain displacement, in this case is A, we let it go. So we start with initial speed or initial velocity 0. So since the force is acting toward the rest position, then this object will accelerate toward rest position from initial velocity, which is 0, so magnitude of speed is 0, magnitude of velocity is 0, is going to reach the maximum speed, or is going to reach at a rest position the maximum magnitude of velocity. Now, why is maximum? Because after this rest position, this object is going to start compressing the spring. As you know, the spring direction is going to be always toward the rest position. So it's going to trying to stop that object from moving. And when it reached the maximum compression, speed is going to be 0, or magnitude of velocity is 0. So this will continue pushing back, going to the rest position again, but this time with a maximum speed or a magnitude of velocity, which is going to be maximum, but direction is going to be in opposite direction. And because of inertia, this object will move to the maximum point and will continue to move back to rest position, and this cycle will continue. So how is the speed of the block related to energy transformation? We're going to talk later on about two types of energy transformation in this case, which is a elastic potential energy and kinetic energy. The constant of proportionality K is called the spring constant of the spring, and it corresponds to the stiffness of the spring. So that means the stiffer the spring, the larger the value of K, and the larger the force required to extend or compress them. So in this experiment, if you have that object attached to a spring, it's going to pull down because of the gravity. So that means that this spring is going to displaced, is going to extend from the rest position at a certain displacement, in this case delta L, which depend on a mass of the object, but will depend on a constant of proportionality or spring constant. The smaller the K, the bigger the displacement. So a spring that obeys Hooke's law exactly is called an ideal spring, and no internal or external friction acts on it. Let's do a practice problem applying Hooke's law. A spring hangs at rest from a support. If you suspend a 0.46 kilogram mass from the spring, its deflection is 0.9 centimeter. Determine the spring constant. So what is given? Mass is 0.46 kilogram. Displacement is 0.079 meter. And spring constant is required. So we can draw a free body diagram. Since that is in equilibrium, we can say that force that is acting up is cancelled by force of gravity, or force of gravity is cancelled by elastic force, whatever is easy for you. So we can say elastic force is positive up minus Fg, which is negative, is down, is equal to 0. But elastic force is minus K delta X minus mg is equal to 0. So what we're looking here is solving for K. So K is equal minus mg divided by delta X. So that is equal to minus times 0.46 kilogram minus 9.8 meter per second square divided by 0.079 meter. We can solve for K, which is 57.1 Newton per meter. B. Calculate the displacement in centimeter of the same spring when 0.75 kilogram mass hangs from it instead of that 0.46 kilogram. So we know now the spring constant is a 57.1 Newton per meter. So everything else, mass this time is 0.75 kilogram. So what is displacement? So we know that already formula, we just use that formula that we had. So K is equal minus mg divided by delta X, and we can solve for delta X, which is mg divided by minus mg divided by K. And then we can plug everything that we know, minus 0.75 kilogram times minus 9.8 meter per second square divided by 57.1 Newton per meter. And then we have 0.13 centimeter or 13 centimeter. 0.13 meter or 13 centimeter. C. Suppose that 0.75 kilogram mass is pushed upward, compressing the spring. Calculate the net force on a mass when the spring is compressed 5.3 centimeter. So what is given? Spring constant we know already, is the same spring, by the way. So once we know the spring constant is not going to change because we didn't change the spring. It's a 57.1 Newton per meter. Now displacement, as we said, is compressed 5.3 centimeter, which is 0.053 meter. So what is force? Net force. We can draw a free body diagram. So since that we are compressing it up, that means that elastic force is opposite of up, which is going to be down. And obviously force of gravity is down. And this is free body diagram. So we don't know that is in equilibrium or not. Obviously not. But we don't know the net force. That's what we're looking for. So we know the net force is equal to Fe, which is elastic force, which is a minus Kx, plus Fg, which is equal to mg directed down for force of gravity, and for elastic force is a K delta X, which is directed down this time. So we can sum of all forces equal 10.4 Newton down. So we can plug those numbers in the, we have 0.75, 9.8, and 5.71 Newton per meter times 0.053 meter. Both of them are down. So sum of all forces is equal 10.4 Newton down. Determine the acceleration of the mass at the position given in C. So second Newton law, we know F net is 10.4 Newton. We just calculated it. Mass is 0.75. So acceleration is required. So sum of all forces is equal ma. We are solving for A, which is sum of all forces divided by m. 10.4 Newton down divided by 0.75 kilogram. That will give you acceleration 14 meter per second square down. So as we know, jumping on a trampoline requires energy transformation. So we have a transformation between kinetic energy, gravitational potential energy, and elastic energy. During the jumping, springs in a trampoline are stretched and returned to a rest position, and the cycle will continue. The transfer of her kinetic energy into potential energy stored in the trampoline. Elastic potential energy is the potential energy due to stretching or compressing of an elastic material. So we did that experiment with a box, and we found out that when a displacement was positive, spring force was negative, and when a displacement was negative, spring force was positive. So we can actually draw it, we can graph the relationship between a displacement and a spring force, and you clearly see that here is a displacement, is negative, so force is positive, and here is a displacement which is positive, now force is negative. Force is negative. Now we know that the area under the graph represents work done. So we know that area under the force displacement is work done by that force. So we can say work is equal sum of the triangle, which is half of the x, k delta x. And both triangles actually are the same. We can say that work on each side is equal half of the k delta x squared. So that would, we know that work is equal change in energy, and this time the energy is elastic energy, and we find the formula of calculating elastic energy, which is half of the k delta x squared. Let's do a practice problem with elastic potential energy. A 42 kilogram teenager balanced briefly in a pogo stick, causing the spring in a stick to compress downward by 0.18 meter. Determine the elastic potential energy of the teenager. So mass is 42 kilogram, displacement is 0.18 meter, elastic energy is required. First, we need to calculate spring constant or coefficient of proportionality. So we know the formula K is equal minus mg over delta x, which is a minus 42 kilogram minus 9.8 meter per second squared divided by 0.18 meter. That is 2,287 Newton per meter. Now we are ready to calculate elastic potential energy, which is half of the k delta x squared. So K is 2,287 Newton per meter, and delta X is 0.18, that in part of 2. And if you plug that in the calculator, you'll get 37 joule of energy. Let's talk about periodic motion and simple harmonic motion. Motion that repeats itself is called a periodic motion. Now suppose a block is connected to a spring and a block is moving on a frictionless surface. We know as a block moving past the equilibrium position, its speed will decrease because of the increasing the elastic force that opposes the motion. So we have seen this. If we stretch the spring in a frictionless surface, then the object, the block, is going to be pulled by elastic force, which is going to pull it toward a rest position. So as it reaches that rest position, because of inertia, the object will keep moving and compressing the spring, reaching to the certain maximum compression force, which this force will make that object to slow down and reach to a complete stop at that moment, and is going to push toward the rest position again. And when it reaches the rest position, it's going to continue to move because of inertia, because of the elastic energy is turned into a kinetic energy, and that is energy transformation. And when it reaches the maximum stretch now, then elastic force is pulling again toward a rest position as it did before. And if you see, it's a cycle, and this cycle continues. So this motion will repeat itself, and that's why it's called a periodic motion. In the experiment that we did, the block continues to move past the equilibrium point and stop when the spring is fully stretched with a positive displacement plus A, or fully compressed with a negative displacement negative A. So amplitude A is the maximum displacement in a positive direction or is in a negative direction. This back and forth motion is an example of simple harmonic motion. In this motion, a mass on a spring has a displacement as a function of time that is sine or cosine curve. Here, A is called amplitude of motion. So if we do this and we can draw that motion of that block in time, you're going to see that block is going to move back and forth, but is going to be as a sine or cosine curve. Here is an experiment. If we can compare that simple harmonic motion of the spring and a block, you're going to see that if we have a block connected to a spring and we can stretch the spring at this point here, is going to move back to the rest position, and because of inertia is going to go and compress the spring, and the spring is going to push back and push toward the rest position, and because of inertia is going to go to other position. So that means that, or if we have to talk about an energy transformation, so that means that if we pull it at this point here, we have an elastic potential energy. And if we let it go, this elastic potential energy, it is going to change into an energy of moving block, which is kinetic energy. And because of the block here does have a kinetic energy, is going to transform by pushing, by compressing the spring, is going to be transformed into elastic potential energy and reaching at this point maximum elastic potential energy because it's maximum compression, when kinetic energy is zero because it stops at this point and is moving back toward the rest position, giving kinetic energy, the maximum kinetic energy at this point here when elastic energy is zero because displacement is zero. And this energy transformation goes back and forth in a what we call simple harmonic motion. Now let's compare this to a uniform circular motion. So let's say that we have a reference point here and we have a light here where that reference point will cast the shadow here. And as the reference point is moving to this position here, the shadow is going to be at this point, and as the reference point moves to this, shadow is going to be on this. So we had initially here, went to this point, went back, and when that reference point is going to be here, it's going to go back to in middle, and when a reference point is going to be back to where it was, so the shadow is going to be. So if you see that it is a simple harmonic motion, it is a repeated motion, it's a periodic motion that the reference point at an object that is moving at a circular motion, it is moving at a simple harmonic motion exactly the same as a block that is moving, that is attached to a spring. So again, simple harmonic motion is a periodic motion in which the acceleration of the object is proportional to its displacement. So that means when the displacement is maximum, then acceleration is maximum because the force reaches the maximum at a maximum compression. When it goes to a zero, then acceleration is 0 by going to another side on a compression, since that elastic force is at the maximum when it's a maximum compression, acceleration based on the second Newton law is going to be maximum. So that means acceleration is in a direct proportion with displacement. So this is a simple harmonic motion. And we talked about this as well as a reference point as moving in a rotating frame of reference. So both are undergoing simple harmonic motion when acceleration is proportional to its displacement. Now let's compare two motions. A uniform circular motion of the reference point on the rotating CD and the simple harmonic motion of the mass that is connected to a spring that is moving back and forth in a simple harmonic motion on a frictionless surface. So what would be acceleration related to that motion? Let's see. Let's start with a uniform circular motion first, because we know already a relationship between period t of that motion and centripetal acceleration. Centripetal acceleration is equal 4 pi square r over t square. So we can solve for t square, which is 4 pi square r over ac. And we square root both sides, and we have t is equal to 2 pi square root of r over ac. Now r here is equal at amplitude of the motion of the simple harmonic motion, and we can replace that with t is equal to 2 pi a divided by ac. Now, what about this acceleration of that mass that is moving in a simple harmonic motion because of the elastic force? Based on second Newton law, that acceleration is equal force, elastic force divided by mass. But we know elastic force is minus k delta x divided by m. And we do a series of transformation here. We can actually move ax down, and we move m up and k down. So it's like cross multiplication. And we'll get this. So delta x over ax is equal m over k. But delta x is amplitude, right? So that means that it's a over ac. But remember that a over ac we already found. So we can say period is equal to 2 pi a over ac, or t is equal to 2 pi and a over ac is equal m over k. So this is very important, because now this period of periodic motion will depend on a mass of the object and on a stiffness of the spring. So t is equal to 2 pi square root of mass over spring constant. And we know now actually that those formulas that relate simple harmonic motion and uniform circular motion. And we know the shape of that motion, which is a sine or cosine curve. Here is a practice problem with a simple harmonic motion. The diagram shows two identical masses attached to two identical springs, and those are resting on a horizontal frictionless surface. Spring 1 is stretched to 5 centimeters, and spring 2 is stretched to 10 centimeters, and the masses are released at the same time. Which mass reaches the equilibrium position first? What do you think? So although there is no calculation here, so it is already given amplitude 5 centimeters and 10 centimeters, the acceleration is not given, and you don't really know, and you don't need to know, because what is asked here is a period. So time to go to a rest position from the maximum point to rest position. Now we know that this period is equal to 2 pi square root of m over k. Interesting thing is mass are identical and k, the spring, are identical. So that means spring constant is the same. So that is not amplitude here or displacement. So the period does not really depend on amplitude or a displacement. Depends only the mass and the k, and those two are the same. So that means that they do have the same period. And if you want to graph it, then you're going to see something like this. So they have the same time returning to that rest position. So because the k and m are the same, the system have the same period, and based on this formula. So they must return to equilibrium at the same time. The frequency and the period of simple harmonic motion are independent of amplitude. So the answer is they will return to equilibrium at the same time. And it's very clear here that from this one. And here is a last practice problem for this section with simple harmonic motion. When a diving board bends, the restoring force due to the board elastic properties obeys Hooke's law for an elastic material. Suppose a diver of mass of 85 kilograms stands on a diving board with a spring constant of 8.1 times 10 to the power of 3 Newton per meter. The mass of the board is much smaller than a diver's mass, so it's negligible. Calculate the period at which the board vibrates. So mass is 85 kilogram and spring constant is 8.1 times 10 to the power of 3 Newton per meter, and period is required. So a very simple problem solved by a formula. T is equal to 2 pi square root of m over k. We have everything. You plug those numbers into that formula, plug those numbers in the calculator, and you're going to have period is 0.64 second. And this is it for this section 4.6, elastic potential energy. Section 4.7, springs and conservation of energy. In this section, we're going to talk about conservation of mechanic energy, which this time includes a new energy that we just learned, elastic potential energy. So now that we learn elastic energy, which is a part of mechanical energy, we can say the law of conservation of energy include that energy now, which is elastic potential energy. So we can say that law of conservation of energy states that energy is neither created nor destroyed in an isolated system, but can be transformed between kinetic energy, gravitational potential energy, and elastic potential energy and other forms of energy. Energy loss due to the effect of such a friction, air resistance, and thermal energy and sound can be ignored as negligible. Now let's apply that law of conservation of mechanic energy in one problem that involves all three types of energy: kinetic energy, gravitational potential energy, and elastic potential energy. A model car of the mass 5 kilogram slide down a frictionless ramp into a spring with a spring constant of 4.9 kilonewton per meter. So that means 4.9 times 10 to the power of 3 Newton per meter. The spring experienced the maximum compression of 22 centimeter or 0.22 meter. Determine the height of the initial release point. So what I have here, we have a mass, we have spring constant, we have displacement, which is a maximum displacement at point 2. And since that is a maximum displacement, speed at point 2 is 0. So that means the kinetic energy at point 2 is 0. So what we're looking is a height at point 1, or what we label here as the delta y. So law conservation of energy, we can say total energy on point 1 is equal to total energy on point 2. So on point 1, we have all mechanic energy, which is gravitational potential energy plus kinetic energy plus elastic energy, has to be equal to all mechanical energy at point 2, which are gravitational potential energy on point 2 plus kinetic energy on point 2 plus elastic energy on point 2. Now we can write the formulas for each those energy. So gravitational potential energy is mgh, in this case is h1. Kinetic energy at point 1 is half of the mv1 square, and elastic energy is half of the k delta x1 square. That is equal to mgh2 plus half of the mv2 square plus half of the kx2 square. But remember, at position 1, we have height, which means the mgh1 is not 0. However, the car starts from 0. That means this the kinetic energy will become 0 because speed is 0. And now there's no spring at all at point 1. So that means elastic energy is 0. At point 2, it reaches the bottom reference point. So that means gravitational potential energy at point 2 is 0. And obviously it reaches the maximum compression. That means that speed at point 2 is 0. So everything that is here ends up only with 2 mgh1 is equal to k delta x2 square, which is x maximum. Now we can solve for h1, which is delta y in this case, is equal k delta x2 square over 2 mg. And now we have everything. We can plug those numbers into that formula. 4.9 times 10 to the power of 3 newtons per meter times 0.22 meter, all in power of 2, divided by 2 times 5 kilogram times 9.8 meter per second square. So we can plug that in calculator and we can find delta y is equal to 2.42 meter. B. Calculate the speed of the model car when the spring has been compressed 15 centimeter. So mass is 5 kilogram. Spring constant again is 4.9 times 10 to the power of 3 Newton per meter. Maximum compression was given 0.22 meter, and the other compression at the point 3 is 0.15 meter. Speed at a point 3 is required. Now we can say total energy on point 1 is equal to total energy on point 3, but we shouldn't do that because total energy on point 1 is already calculated value. So always try to avoid using calculated values on solving a problem, because if you made a mistake at A, you're going to carry that mistake at B. So if you have choice, in this case, yes, you do. You do a total energy on point 2 is equal to total energy on point 3, and we write the same thing. Gravitational potential energy on point 2 plus kinetic energy on point 2 plus elastic energy on point 2 is equal to gravitational potential energy on point 3 plus kinetic energy on point 3 plus elastic energy on point 3. Thing is, there are few things that gravitational potential energy on point 2 and on point 3 are 0 because they are in a level. Then remember that speed at point 2 is 0. That makes kinetic energy on point 2 0. And now we can solve for V3. So what is left there? On the left side is left kx2 squared because we can get rid of halves. And on the right side, we can get rid of those two halves. And what is left here is mv3 squared plus kx3 squared. So that's why we write it here. And then we can solve for v3. So v3 is square root of k x2 squared minus delta x3 squared. Okay, stop here for a moment because that is something that I want to make sure you understand this, because many people actually made that mistake. They put square here instead of delta x2 squared minus delta x3 squared. It is not x2 minus x3 all squared. Okay, because that is going to be wrong. It will give you a wrong result. So make sure you don't make that mistake here. Okay, so you have everything there, and you can plug those numbers, and you can find V3 is equal 5.04 meter per second. C. Determine the maximum acceleration of the car after it hits the spring. Okay, so sum of all forces is equal to ma, and when it hits the spring, that's a maximum elastic force with a maximum displacement, which is 0.22 meter. So we can solve for actually acceleration, which is acceleration is equal to minus k delta x divided by m. So we have all the values there. All what we need is 4.9 times 10 to the power of 3 Newton per meter, and maximum displacement is 0.22 meter forward. In this case is on the left. Obviously the car moves forward, and divided by 5 kilogram. So acceleration is 215.6 meter per second square backward. In this case, it is on the right because the car is moving on the left. When we talk about ideal spring, we said that ideal spring is a spring that obeys Hooke's law. That means there is no internal or external friction on that spring. An ideal spring would never lose energy and would continue with a simple harmonic motion forever, or as long as you did not disturb it, or there's no external force act on it to make it stop. A perpetual motion machine is a machine that can operate forever without restarting or refueling. An ideal version of the Newton's cradle would be a perpetual motion machine because it would never lose energy. That would be theoretically, because obviously in practice there is no such a thing as a perfect sphere with a perfect elasticity. So no internal resistance or friction. And on those strings, there is a resistance there as well, and air resistance as well. However, there are some of those Newton's cradle, that are made with a very good steel, and they kind of last for a while, fairly for a while. So you can see that transformation of gravitational potential energy into kinetic energy, into elastic energy, and again into kinetic energy, into gravitational potential energy, and vice versa. If you have a pendulum swinging and there's no friction, no air resistance, no internal friction on a string, you can expect that pendulum will swing forever. It is undergoing simple harmonic motion forever, but the friction is real. The friction in a real periodic system is referred as a damping, and the harmonic motion of the system affected by friction is called damped harmonic motion. The system still oscillates, but amplitude of oscillation gradually decreases with time until it comes to complete stop. So we have three types of damped harmonic motion. One, it is underdamped, which is more realistic of the springs. So they are going to oscillate and it's going to come to complete stop eventually because of the friction internally and externally friction. However, in the mechanic, they are more interested on two types of damped harmonic motion, over-damped and critically damped, especially for springs that made shock absorbers in a car. So you don't want, because of the bumping road, you don't want to jump back up and down if that spring is a very good spring that make up those shock absorbers in a car. So the shock absorbers on a car serve to dampen its coiled springs. The goal is usually to have car respond to bumps in the road as critically damped oscillator. Shock absorbers enable the tires to move up and down over the bump in the road without directly passing that vibration to the car body or to the passenger. So basically, you kind of avoid that bumpy road if you have very good shock absorbers, and when they are defective, that is something that you're going to feel in a car is very bumpy when it goes. And that's pretty much is about 4.7 and for all entire chapter 4. Have a good one, everybody.